we're picking up where we left off in chapter 12, and we're going to start off by talking about sinkholes. So sinkholes are nothing more than a depression that can be found in regions that are underlain by soluble rock. There's two ways that they can form. First way is that soluble rock below the soil is dissolved by that seeping water. Eventually that soil is removed and you have a shallow depression that will connect to form solution valleys. Second way is you have the cave roof collapse, and it's going to generate, and you will have a very steep-sided crater. This picture shows you a sinkhole in Florida back in 1981. That developed. It destroyed a house, it destroyed a swimming pool, and some other smaller buildings. Caves are naturally formed subsurface openings that is generally connected to the surface, and they're large enough for a person to enter. Some of the well-known caves are Mammoth Cave in Kentucky, which you see a picture of. We have Carlsbad Caverns in New Mexico and a few others. The difference between a cave and a cavern is basically a large cave or a system of interconnected caves. Now, the way the cave is formed, you have groundwater that percolates through the zone of aeration. It is going to dissolve the carbonate rocks. Your fractures will be enlarged. Your bedding planes will be enlarged. You will hit the water table, and your water table will start to migrate towards your surface streams. It is then going to create those horizontal passageways. The lowered streams create a lowered water table, and you get a new formation of caves. And you can see this process going through picture A, B, and C. In picture A, it shows you that groundwater percolating downward through the zone of aeration and flowing into the zone of saturation. In picture B, you see your stream has eroded deeper, and groundwater moves along the surface, lowering the water table, forming these interconnected horizontal passageways that you see in dark brown. And in picture C, you see we even have a deeper erosion of the stream, creating a deeper valley. Notice how your water table is dropped from picture B to picture C, and you get these abandoned channelways of interconnection that forms your caves. Some deposits that we see in caves that you can see in the picture I have for you. Dripstone is basically just a term we use for calcite deposits. Stalactites hang from the ceiling. They're composed of that calcite precipitation from the dripping water. Stalagmites, you can see in the picture, they form from drips that have hit the cave floor. A column is when your stalactite and your stalactite meet. A drip curtain is that vertically sheet of rock. And then a travertine terrace is caused by water flowing over the cave floor. So beautiful examples of this can be seen in the caves I mentioned in the previous slides. Here's another great picture of, you see the stalactites, the stalagmites, you see the curtain effect, you see the terraces there, you see the column where the two stalactites and stalagmites have met. So how can we modify groundwater? Well, we have been using groundwater and we haven't been concerned with the long-term effects. So about 20% of all our water that's used in the U.S. is groundwater. So If we don't make some modifications, we could have some serious consequences to deal with. We could see a lowering of the water table. We could see saltwater incursion. We could see subsidence, and we could also see some contamination occurring. So what do we mean by lowering of the water table? Well, if I take out groundwater at a higher rate than it's replaced, I'm going to lower the water table. The High Plains Aquifer that you can see in this picture, it underlies about 450,000 square kilometers of land. It accounts for about 30% of all our groundwater that's used for irrigation in the United States. So we did a study in 2017, the U.S. Geological Survey, and it showed that about 9% decline in recoverable water from that storage from pre-development before 1950. So you can see the color coding in this map. The dark blue indicates a decline greater than 15 meters. The brown is between 15 meter decline and a 3 meter rise, and then the light blue is a greater rise of 3 meters. So it's something to be conscious of. We don't want our water table to get significantly lower. Saltwater incursion is caused by excessive pumping of groundwater in our coastal areas, and this is a big problem in coastal communities. What will happen, you form a lens-shaped body above the salty water. So excess pumping is going to draw your salt water into wells. You're going to get a cone of ascension. And you can see our cone of ascension right here. So recharging of our wells and ponds can actually counter that effect, because we're pumping groundwater back in, so we're lowering the interface between our fresh water and our salty water. Subsidence is another problem that we encounter when we remove groundwater. And this is going to be seen in poorly consolidated sediment or sedimentary rock that tends to pack close together. If we take out too much oil from our ground, we can cause subsidence. And an example of that is in the San Joaquin Valley in California. This picture shows the Leaning Tower of Pisa. It leans because of groundwater withdrawal. And then finally we can have groundwater contamination, and that is the common source. The most common source of groundwater contamination that we see is by sewage, by landfills, by toxic waste disposal sites, and by agriculture. Because once we put those pollutants in the groundwater, they're going to spread through all those pore spaces, and containment is difficult, if non-existent, basically. So anything that goes in the ground can seep through and get into your groundwater. Some other groundwater activity we have is our hydrothermal activity, hydro being heat, or hydro being water, and thermal being heat. So hydrothermal is referring to the hot water. So that's when your groundwater gets heated, and any surface activity is a result of that heating. What you're seeing in this picture is what's known as a fumarole, and that is a volcanic gas discharge. In terms of you seeing the steam, and that's the result of your groundwater being hot. Your hot springs. Hot springs are classified as any water that's greater than 37 degrees Celsius. Some can be much hotter than the boiling point. So basically what happens is your groundwater is flowing over magma or igneous rock, and it picks up that heat and travels, and that heat travels with the water. So we could also get that heat from deep circulation in the geothermal gradient. This picture shows Morning Glory Hot Spring in Yellowstone. It is one of the more colorful hot springs. It is fringed by the multicolored mats of heat-loving cyanobacteria and your algae mats. That's what gives it the different colors. Hot springs you might be familiar with are those that are in Arkansas, and those are the result of that water flowing over those hot igneous rocks. And then something we've heard about is our geysers. So a geyser is basically a hot spring that periodically will eject hot water and steam. This picture shows the more famous one of Old Faithful in Yellowstone. What happens is you have that surface of interconnected fractures that reach your hot igneous rock. That's going to cause that groundwater to be heated. We know hot water is less dense than cold water, so that hot water has to rise. As it rises, it's going to erupt in form of that steam that you see. So basically, a geyser is like a volcano, but instead of lava, you're dealing with hot water. This picture kind of shows a good anatomy of a geyser. So you can see the dotted line is your water table. Notice that red at the bottom is your hot igneous rock. That heat raises upward. So you can see how that water gets heated from the igneous rock and will eventually erupt as your geyser. So your hot springs and your geysers, they do contain a lot of minerals that will precipitate at the surface. It depends on what material that groundwater is actually flowing over. If that groundwater contains calcium carbonate, then you're going to see some travertine or calcareous tufa. Both are basically varieties of limestone that get precipitated. So in picture A, you're seeing travertine. In picture B, you're seeing a silicon dioxide deposit. Now, geothermal energy is one form of our alternate energy sources, and geothermal energy is produced from the Earth's internal heat. It's a very good form of energy in that it's non-polluting, and it is and can be used as a source of heat to generate electricity. It is used in Iceland. It is used in some areas of the United States, Mexico, and so forth. Okay, this ends chapter 12, part 2.